Well, howdy there, and thank you for tuning in to our discussion of Learning Target 5.3 in chemistry. In Learning Target 5.3, we're going to define an ionic bond and explain how it's formed. You can find that in section 7.1 of your book. If we know the nature of two ions, we're going to predict the formula of an ionic compound, section 7.2 and 7.3, and we're going to describe lattice energy and explain how we can relate the size of ions to lattice energy. So here we go. What is an ionic bond? An ionic bond is defined as the electrostatic force that holds oppositely charged particles, known as ions, together. We defined bond earlier in the unit as a force that holds two atoms together, so we're just making this a more specific definition of bond. This is an ionic bond. Electrostatic means a force between a positive and a negative. If we have a positively charged ion like Na+1, it could form an ionic bond with Cl-1 because they are oppositely charged particles and there should be an electrostatic force between them since they are equally but oppositely charged. Those dots right there would represent that force, so that would be your ionic bond. Ionic bonds are different than maybe what you have learned about as a bond before, where electrons are shared. There are no electrons shared in an ionic bond. It is simply an attraction between a positive and a negatively charged ion. No sharing. In fact, we're going to learn that there's actually stealing happening. When you have an ionic bond, one of those components is always going to be a metal. In this case, it's the sodium, and it's always going to be the cation, the positively charged, and one nonmetal, which will be your anion. So I'm going to go ahead and write that in here. Your metal is going to be the cation, and your nonmetal is going to be the anion. The difference in electronegativity between the metal and the nonmetal must be more than 1.7 to be an ionic bond. And we're going to mark that on your periodic table. That's on the front. Down towards the bottom, you'll see a little chart that says % ionic character. And you have that, and you have a difference in electronegativity. And I can't remember, I think the difference in electronegativity is actually on the top of your chart. But anyways, when you get to 1.7, that should indicate a % ionic character of above 50. And so we want to make a line, a heavy line right there, that anything above 1.7 in electronegativity difference is going to be considered an ionic bond. And we'll talk about what that means here in a second. But make sure you mark that on your periodic table. If you need to pause right now so that you can do that, go ahead. So, ionic bonds are going to be formed when a more electronegative atom steals an electron from a less electronegative atom, resulting in the formation of oppositely charged ions. It turns out that at that 1.7 electronegativity difference, an atom actually has enough power to pull an electron off of another atom. So when that difference gets big enough, then an electron will actually be stolen. So an example of this might be between something like potassium and fluorine. Now, potassium has an electronegativity on your periodic table of 0.8, and fluorine is 4.0. So remember, the electronegativity scale goes from 0 to 4.0. 0 meaning no electronegativity, so no desire to attract an electron, to 4.0 meaning is a very good electron attractor. I like to think of it as tug of war. So somebody with a really low electronegativity would be like a real tug of war weenie, like just a sure bet that you would win against that person. Somebody with a 4.0 ranking would be somebody that'd be really good at tug of war. So think of it that way. Now, in a fight between K and F, that difference in electronegativity is equal to 3.2. And if you look on your % ionic character, that is well above a difference of 1.7. In fact, a 3.2 gives us a 92% ionic character. So anything above 1.7 is ionic, so this would form an ionic bond. So what would happen is fluorine would be stealing electrons from potassium. So when there is such a lopsided fight, one can peel an electron off of the other one. And that's how an ionic bond is made. So let's look at how this works in electron transfer. And here's a little joke while we're talking about this. It says, how ionic bonds really form. Do you take this anion to be your lawfully bonded wife? I do. Here's my valence electron, baby. See, he's giving her his valence electron. He says, I love you. We'll be together forever unless we're melted, dissolved in water, or I find a cation. I'd rather be bonded in a single or double replacement reaction or electrolytically decomposed. It's funny. So let's take, for example, magnesium and oxygen. And I believe in your notes this is different. Your notes say Na and Cl. And I'd like for you to change that. Change it to Mg and O. So you can see here that we've got a metal and a non-metal. So that gives us an indication that we would form an ionic bond. And magnesium has an electronegativity of 1.2. Oxygen has an electronegativity of 3.5. And that is a difference of 2.3, which means this is going to be an ionic bond. So if I form an ionic bond between these two, and I look on my periodic table, magnesium has 2 valence electrons, so its electron dot diagram would look like this. Oxygen has 6 valence electrons, and its electron dot diagram looks like this. Now what we're saying here is that the electrons should be stolen from magnesium to oxygen. So when that happens, because of that difference in electronegativity, because oxygen is such a stud and magnesium is such a weenie, oxygen is actually going to peel those electrons off and use it to fill its valence electrons. When that happens, after that occurs, magnesium is going to be more stable actually, because he's like, all right, I'm fine with that. Take my valence electrons, I don't care, and get a +2 charge. And oxygen, gaining 2 electrons, is going to have a -2 charge. In an ionic compounds must be neutral overall. That means there can be no charge, and this kind of goes to what we were doing yesterday in your activity. So what we want to look at to write the formula, so one formula unit, means the smallest piece of this has how many of each ion. Now the way that they are written right here, I have a +2 and a -2. If I had one of each, my charges would be balanced. So if I have a +2 and one of them, that would give me an overall +2, and a -2 and one of them, I would have a -2, and a +2 and a -2 gives me a 0 overall charge. So one formula would be Mg1 and O1, and since that's neutral, we can just write that as MgO. So that is the correct formula for a compound that's formed between magnesium and oxygen. Let's do another one. If I have strontium and fluorine, and again, I think this is different than in your notes. Let's go ahead and change it. Strontium has an electronegativity of 1.0 and fluorine is 4.0. So that's a difference in electronegativity of 3.0, which means that this is an ionic bond. If I look at my difference in electronegativity, its character is 89% ionic, which means it's very ionic. Strontium is quite a weenie in electronegativity, and it has 2 valence electrons. Fluorine is a stud and has 7. And because fluorine is a stud, it's going to rip away a valence electron. But here's the thing, it's not going to rip both valence electrons because it only needs one more to be perfect. So what happens here is that there's actually a second fluorine that will steal the other electron. And this works out really handy because if strontium loses both, which it would really like to, it gets a positive 2 charge, and each of these fluorines gets a negative 1 charge. So one formula unit, if I had Sr plus 2 and F minus 1, I would get 1 strontium, that would give me a plus 2 charge, and 2 fluorines times negative 1 would be negative 2, and that would give me a 0 charge. So I would have Sr plus 2, F minus 1, 2, or Sr F2 for my formula. So let's back up a little. C and O. Now one thing I want you to notice right away is that I don't see a metal here in our pairing, but we'll go ahead and try this anyway. 2.5 is carbon's electronegativity, and oxygen's is 3.5. Now that's a difference of 1.0, so there's going to be no ionic bond formed. That's going to be a different kind of bond. So we can't do this the way we normally would, and we're going to have to say just no ionic bond formed. There's going to be no pluses and minuses, no ions formed here. Well, let's talk about when we see a polyatomic ion present in the formula. Now really this should be up here, OH minus 1. So when we form a polyatomic ion, what we can do now is look at the ion's charge of each species. So aluminum I see has 3 valence electrons, so it would be a plus 3. OH would be a minus 1. So right now these are not balanced. So what I can do here is find the least common multiple to make these so their charge is balanced. In other words, what can I get down here that I could get for both of them? And the answer is 3. So down here if I had 1 aluminum I could get a plus 3. And if I had 3 OH minuses, I could get a minus 3. And now think back to your activity from yesterday, or that you did earlier last week if you were in Mr. Mester's class. If I had 1 aluminum, that's fine. But if I wanted 3 of this entire species, I'd need to put parentheses around it. So plus 3 and minus 1. Well, actually that should be inside. I'd want 3 of those, not just 3 hydrogens. So the question to ask yourself is if I take those parentheses away, does that change what I'm trying to say? And it does. Here I'm saying I have 3 of the entire OH group. Here I'm saying I just have 3 hydrogens. So it's important that I put those parentheses on to indicate that I have 3 of everything inside, not just the H. So that would be my formula unit. It would have 1 Al and 3 OH minuses. Finally, sometimes you have transition metals, and transition metals are generally going to form ionic bonds even if their electronegativity values don't work out. So in other words, if you see that it's an ion on the back, or that it has an Ich-Us charge, it's going to form an ionic bond, even though its electronegativity might not say so. For example, if you look at iron, iron's electronegativity is 1.8. Sulfur's is 2.5. That is only a difference of 0.7. However, this is going to form an ionic bond, and that's kind of weird. The reason it's kind of weird is because those transition metals don't really behave themselves like representative elements. So if you have a transition metal and you have one metal and one nonmetal, you can just assume it's ionic and you should be able to find the charge on the back. So basically, if it has a charge on the back, you can assume that it's going to be an ion. Alright, so iron Ich and sulfur. Iron Ich is going to be Fe, and that is going to be the higher of the 2 charges, so that's going to be a plus 3. And S is going to be something with 6 valence electrons on the front side, which means it's going to be a minus 2. Now, something to look at really quickly is that for sulfur, you might be tempted to say it's got 6 valence electrons, so it's a plus 6. And there's a problem with bonding these two things together. And the problem is that with a +3 and a +6, there is no reason that they would be attracted to each other. In fact, they would move as far away from each other as they could get. So in order for you to have a bond between two things in an ionic bond, you would have to have one positive and one negative. So sulfur having 6 valence electrons, it's a lot easier for sulfur to pick up 2 electrons than to lose the 6 it has. So it's going to become a -2. So always be on the lookout that your charges are opposite. If I look for the least common multiple between these two things, I'm going to need to make that a 6. So I can make a +6 and a -6 by having 2 irons and 3 sulfurs. When I do that and my charges are neutral, I should end up with Fe2S3. Now I want to show you what happens if we change this to Fe us and S. If I have a Fe +2 and an S -2, then I only need one of each thing because they're already canceling each other out. So the formula between these two things are different, and that makes sense because something that has the iron ick ion in it is going to be a different and act differently than something with the iron us ion in it. So I would like for you now to go on to the back of your periodic table where you have your polyatomic ions. And I would like for you, just do this on a piece of scrap paper or in your notes or whatever you want to do. And I want you to try to write the formulas for these two, and then you're going to pause it and try it. So the first one I want you to try is, let's see, let's have you do I know this is a really hard decision. Let's have you try cesium and oxygen. And then let's have you try lithium and phosphate. So pause and then give it a try. Okay, these should be your answers. There were no parentheses that you needed in this case because adding parentheses wouldn't change anything about what you're trying to do. So in this case, CS was +1 and O was -2. So you needed to multiply your CS by 2 to get +2 and your O by 1 to get -2, and you ended up with CS2O. If you had parentheses around the CS, you really shouldn't. If you take those away, then it wouldn't change anything about what you're trying to say, so that means they're not needed. And yes, you're going to be marked down if you have parentheses when you don't need them, so don't get parentheses happy crazy. Here, lithium is +1 and PO4 is -3, so you need 3 of those and 1 of those. And since you don't need more than 1 of that PO4, you don't need it to put it in parentheses because that's not meaning anything different than just having PO4 all by itself. So the key to these is practice, practice, practice. I have lots of practice problems for you to do. Try those until you get to the hang of it, and then practice some more. Have a great day, and I will see you later.